Alright, today we're going to talk about critical numbers or critical values. And a critical number is something we've been working with for a while. But these are values where the derivative is equal to 0 or undefined. And so what I mean by undefined, it's either it comes to a cusp or a point, if it's a rational function and the denominator is equal to 0. These are what we're going to be looking for. These are what is called a critical number. And so if f prime of x is equal to 0 or f prime of c doesn't exist, then c is a critical number. If you want to find the critical point, you have to find the y value at that x coordinate. So critical numbers may or may not be maximum minimums. We're going to get into that a little bit in the next couple videos. You just have to check the y values or do a sign chart, and I'll show you how to do that in the next video. And please don't forget areas where the derivative might be undefined. Alright, so let's go through several examples. Alright, number 1, part A, we're going to find the critical numbers of our function f of x is equal to 9 times x squared minus 3. And I'm just going to go ahead and simplify this a little bit before we could do anything. Oops. I'm just going to say this is 9x squared minus 27 divided by x, and most of you are going to want to use the quotient rule, and that's fine with me. So let's go ahead and take our derivative. So f prime of x is equal to low times the derivative of the high minus high times the derivative of the low all over low. And so that's equal to 18x squared minus 9x squared plus 27 all over x squared, and that is equal to, let's see here, negative 9x squared plus 27 divided by x squared. And so when we try to find the critical numbers, we're trying to find where in this case, both the numerator and the denominator are equal to 0. So f prime of x doesn't exist where our denominator is equal to 0. In this case, since it's an x squared, so f prime doesn't exist when x is equal to 0. Now we need to check where f prime of x is equal to 0. And so let's set our numerator. Equal to 0. So I'm going to factor out a negative 9. So that leaves me with x squared minus 3. I'm going to set that equal to 0. And that means x squared minus 3 is equal to 0. And that means x is equal to plus or minus the cube root of 3. And so those are my other two critical numbers. Part B, I want to find where f of x is equal to the absolute value of x. I'm going to show you a quick trick. If I have f of x is equal to the square root of x squared, let me write that a different way. Let me write it like that, of x squared. And then if I'm taking the square root of a number, it doesn't matter if I plug in any type of negative number, I'm still going to always have a positive because my squared is going to take care of that. And so the resulting answer is always going to be a positive number. Well, if the result is always going to be positive because of this squared right here, that means any negative number that I plug in is going to give me a positive number. And so what this equal to, in a very bizarre way is this is equal to the absolute value of x. Remember, absolute value means it always spits out a positive answer. Well, so does the square root of x squared. So I'm going to say that my f of x is acting like the square root of x squared, because they both spit out the positive answers. They both spit out the same y positive answers. And that's a little bit easier to take the derivative of. So I'm going to do the parentheses x squared, and this will be to the 1/2, and let's go ahead and use our chain rule. So f prime of x is equal to 1/2. This becomes a negative 1/2. And on the inside it'll be x squared, and then take the derivative of x squared. This gives me 2x. Well, this is going to be equal to 1/2 times 2x over the square root of x squared. My 2's are going to cancel, and I'm going to be left with x over the square root of x squared. Alright, now let's go ahead and let's set our numerator and our denominator equal to 0. So here let's start with our denominator. And so what values of x make the square root of x squared equal to 0? Well, I'm hoping you're coming up with 0. So f prime of x doesn't exist when x is equal to 0. And similarly, if you set the numerator equal to 0, we're going to get that same answer, f prime of x. If we set that equal to 0, we're going to get still x is equal to 0. And so it's not like we have a double critical point, we just have the same critical point showing up. That x, in this case, f prime of x doesn't exist. This is actually the technical correct one. F prime of x doesn't exist when x is equal to 0. And again, if you remember from our graph, f prime of x comes down to a point and then comes back up. And anything that comes to a point, you can't take the derivative of. Alright, let's find the critical points for sine x. So let's go ahead and take our derivative. So f prime of x is equal to cosine of x. And we're going to set this equal to 0 because we're going to find those values of x that make the cosine function equal to 0. Well, again, cosine is equal to 0 at pi over 2 and 3 pi. And so my critical points are located at x is equal to pi over 2 and 3 pi over 2. Number 2, for f prime of x is equal to cosine squared x divided by x minus 5. How many critical values does f have on the interval from 0 to 10? And so they already gave me the derivative, and so I'm just going to go ahead and plug it into my y equals. And so I have y equals, I'm going to go ahead and plug in cosine, so parentheses, cosine of x squared divided by x minus 1 over 5. Alright, and I'm going to change my window. I want my x min, I'm going to go from 0 to 10, so I'm going to change my x min to 0. My x max is already set to 10. And then let's go ahead and graph. And it's really hard to see because I can't tell how many times it crosses. So I'm going to go back to my window, and it looks like it gets really, really close to 1. So I'm going to change my x min. I'm going to say that's -2, and my y max is 2. Let's kind of zoom in and see what it looks like. And it's still really hard to see, so I'm going to go back to my window. Let's try -1 to 1. There we go. Much better. And if you notice, our function, it goes down, hits about x equals 1, and then crosses the x-axis between 2 and 3. crosses the x-axis again between 3 and 4, but doesn't appear to cross at, it might touch, I don't think so, but it looks like it might touch between, let's see, 1, 2, 3, 4, 5, right about 6. So I'm going to zoom in a little bit further on my y window, and I'm going to say y min, I'm going to say is negative 0.5, and y max is 0.5. I just want to make sure that it's not crossing. And there for sure I know it's not. And so you can see that it's crossing at x is equal to 1, x is equal to maybe 2.5, and then 3.5, and then it does cross again. So it crosses 3 times. And so to answer our questions, how many critical values does f have on the interval? Well, in this case, if we're graphing the derivative, the critical values essentially for the derivative become the x-intercepts, or the zeros, or the solutions. So we have several names for these. And so the amount that you're counting, the amount of x-intercepts that occur on the derivative. So if you want to think about where does the derivative equal to 0, well, that's going to be where y is equal to 0, and that's another name for that, is an x-intercept. So the x-intercepts, there's 1, 2, 3. That means there's going to be 3 critical values for f. So we're just going to write 3 critical values. Doesn't matter what they are. We just want to count how many there were.